Okay, another technical hiccup. I again ran out of room on my phone. Had to go back and delete a bunch of stuff, but hopefully we should have enough space now to complete the rest of the lecture. What was I talking about? Oh, yeah. So the key difference between classical statistics and quantum statistics is that we cannot label quantum particles, right? Every single quantum particle is completely identical. So if I have two classical objects, right, I could tell the difference between them, right? One is tails, one is heads, and even if they were both tails, they're macroscopic objects, right? Maybe one is tarnished, maybe one has a little dent in it, maybe I could go and just write numbers on all of them so I know what each particle is. For quantum particles, for fundamental particles, this is no longer possible because they are fundamental, right? There's nothing about them you can change without turning them into a different type of particle, right? Every electron is completely identical to every other electron, right? Maybe some are spin up, maybe some are spin down, but that's just a matter of perspective, right? If I took a spin up particle and looked at it, upside down, right, it would look the same as a spin down particle, right? So quantum particles are fundamental, and there's in fact no way in principle ever to tell them apart other than saying, well, the one on the left or the one on the right or something like that. So that means that when two quantum particles get close enough to each other, we can no longer say which one was originally which particle, right? So if I have two particles, say two electrons or whatever else, as long as they're fundamental quantum particles, and they're zooming in towards each other, eventually they're going to get within the de Broglie wavelength, right? So they're going to get close enough to each other such that their quantum wave functions overlap, and once that happens, when they come back out, I don't know if this one over here is the same one over here, or this one over here is the same one over here. And in fact, not only is there no difference between the two of them, there's no way to really say that this one even had any kind of history, right? This one now shares the history of both this electron and that electron because, in a way, the universe has lost the information about which particle was which. Did they just fly past each other, right? Did they bounce off and this one came over this way? Well, since we're talking about quantum things, right, anything that we don't know also means that, like, the universe doesn't know, right? So these guys get jumbled up in here, and after this interaction, there's no way to tell them apart even in principle. So when two particles of the same wavelength get within the de Broglie wavelength of each other, technically they become entangled, right? We'll talk more about what entanglement means in future lectures, but they stop being separate physical systems. We say that these particles are indistinguishable. So if these particles are indistinguishable, their probability densities, their wave functions, must be the same if the particles are switched. So suppose we call this particle 1, just because it's the one that started off on one side, and we call this particle 2, right? Afterwards, these labels of 1 or 2 are erased, so we don't know if this is 1 or 2, and we don't know if this one is 1 or 2, right? We don't know that anymore. And that means that when we write down their probability densities, when we write down their wave functions, the probabilities have to be equal if we switch those two particles. Right? So here the only difference between these two things is I've switched the two x's, right? The one that was in x position 1 and the one that was in x position 2, right? Since they're indistinguishable and after this interaction we don't know which one was which anymore, it has to be the case that they're the same. right? Because any difference between these two things would be a difference between the two particles, and that's something that's not allowed, as I've been saying. So this one, the 1s and 2s are switched. Okay, this is all well and good, but this is true under two different conditions. I'll draw this down here. So this is true if x, or psi of x2, x1 is equal to plus psi x1, x2, or if psi of x2, x1 is equal to minus psi x1, x2. Okay? So because I have the absolute value squared, right? If they're exactly the same, then of course they're the same. But if they're the same up to a minus sign, or in principle the same up to some other phase, but the minus sign is the important one. If they're the same up to some minus sign, then they're the same when I look at the probabilities. Or technically here, the probability densities. Okay. So what that means is the wave function can pick up a minus sign or not if we exchange the particles. But what if we have particles that do have some quantum number? Let's say that these are not just electrons. Perhaps there is some thing that can be different about them. Perhaps they're atoms that one is in the ground state, one is in the excited state. Well, then with those two other quantum numbers, and we're going to write psi plus minus, which that'll be clear what that means in a minute. Some normalization factor. So psi of n, x1, psi of m, x2. Right, so now this is similar to us writing this guy here, right? But now those two particles can have some quantum number. Right? In principle, this is possible. Plus minus psi of n, x2, psi of m, x1. Okay, but now, what if we set m equal to n? So if particles have the same quantum number. Well, if those particles have the same quantum number, let's look at this guy here. So I realized I'd skipped kind of a bit of the explanation, so I paused it and went back and collected my thoughts, which this is one of the handy things about teaching this way is I can do that. I should go back and explain a couple more things about this. So this is called the symmetric state, and this is called an anti-symmetric state. Okay, so when I exchange two particles, right, wherever I do that, there's two possibilities. Either the wave function is written symmetrically so that they're the same up to, or they're exactly the same because I have a plus sign here, or they're anti-symmetric, and when I switch them, the wave function picks up a minus sign, right? So there's never any difference in the way I write the probability distributions for these two particle quantum states. So there can't be any difference between having a plus sign there or a minus sign there. So that's how we get to this state here, right? If we can't tell the difference between them being symmetric or anti-symmetric, well, then both things happen, right? That's the nature of quantum mechanics. That if there's no way in principle to tell which of two possibilities there are, both possibilities are realized. So now I add up both of those possibilities, right? I've switched the two particles, right, their positions, and I have a plus sign for the possibility of a symmetric state, or I have the possibility that I've switched them and I've picked up a minus sign between them, right? So over here, this psi of x1, psi of x2, if this ends up being a symmetric state where we take the plus sign, well then we add them together, right? And then it's pretty clear to see that I just end up with this state here, right? But if I have an anti-symmetric state, right, when I switch the two particles, right, so x1, x2, and then I switch them over here to x2, x1, they pick up a minus sign. Okay, so that would be an anti-symmetric state. Now here, the two particles I've switched, I'm not switching the quantum numbers. Okay? So in other words, we've switched the positions of the two particles, but then we have different quantum numbers. Okay, but then we're going to erase that generality in the next step of this calculation, which is the key, not really calculation, more of a demonstration, but we switch the particle positions. Okay, only, not the quantum number. Okay, so but now let's take the case where they are again indistinguishable, right, where they have the same quantum number. What happens? Okay, I would pause and let you guys think and guess and maybe even figure it out, especially if you've done the reading. But since we're on an online lecture and I'm just alone in my apartment with my cat, I can't do that. He's asleep. Lazy cat. So I'll just tell you, which is if we make these the same quantum number, right? Let's say they're the same quantum number, but for a symmetric state. In other words, we're taking that psi plus possibility. Well then, of course, I have 2 psi, so to be clear, now n equals m. So psi n x1, psi n x2, plus psi n x2, psi n x1. All right, then we just get root 2 psi n x1 psi n x2, and then we can just erase that quantum number because it's the same. It doesn't mean anything anymore. And then, of course, we're just back to over here, right? Okay, so that's all well and good. But what if we have psi minus? Well, then we get 1 over root 2 psi n x1 x2 minus psi n x2 psi n x1. And now these two guys cancel out. I just get 0. So what does this mean? Well, we have two possibilities. We have the possibility of the state being symmetric, and we have the possibility of the state being anti-symmetric, which doesn't cause any problems until we talk about particles interacting in this way that have the same quantum number. And what this means is that if we have some particle represented by an anti-symmetric state, if they get within their de Broglie wavelength of each other, right? If they're interacting strongly or bouncing off of each other or something like that, the possibility of them existing that way, essentially, in the same place with the same quantum number is 0. Okay, so maybe pause the video and think about that for a minute, and I'll go through the logic again, right? If we have two possibilities for our quantum state, symmetric or anti-symmetric, right? I write them as a superposition like this, right? Because I have to realize both possibilities because these come out indistinguishable, right? So the joint quantum state of all of those possibilities is given by this wave function. Symmetric or anti-symmetric, same quantum numbers or different quantum numbers depending on if n and m are equal or not. And we see if we have a symmetric state, everything's fine, right? We have perhaps two photons, they come into contact with one another, they're identical, they interact, they go their separate ways, and they get all jumbled up and we don't know which one was which, and that's fine. Okay. Now, if we have a different type of particle that's realized by an anti-symmetric state, right, perhaps an electron or something, well, what happens when we try and get them into that same de Broglie wavelength? Well, it turns out that they can't be made to do that because the probability is 0. So this gives rise to what's called the Pauli exclusion principle. So we talked a little bit about the Pauli exclusion principle in previous classes when we were talking about electrons in different shells of an atom, right? Now, we could only put more than one electron in each shell of the atom if they had different quantum numbers. So in the first electron orbital for the hydrogen atom, right, one proton, and at first, well, let's say helium, a helium atom, okay. So we have two protons, and let's say I put in an electron, and I put it into the first energy level. Everything's well and good. Now what happens if I try to put a second electron in there? Well, that second electron is going to have a different quantum number because if they had the same quantum number, their probabilities of existing would be 0, right? So electrons don't stack in that way because Pauli exclusion principle says that you can't have those particles be in the same place at the same time with the same quantum number. Okay. So the next natural question is, well, which particles are symmetric and which particles are anti-symmetric? Well, we have two categories. We have fermions and we have bosons. Bosons have integer spin, so 0, 1, 2, etc., and they are symmetric in their quantum states. Why this is the case is not something we're really going to talk about. We'll just say that bosons, integer spin things, they are symmetric, right? I can put them in the same place. So photons, perhaps the most obvious example, they have spin 1, right? And I can put as many photons as I like in the same place. Okay. Fermions, on the other hand, have half integer spin, and they follow anti-symmetric statistics. Okay, so the best example of a fermion is an electron. It has spin 1/2, and I cannot put two electrons in the same place at the same time if they have the same quantum number. Okay. So the result of all of this for our quantum statistics is that we need two new types of distributions for quantum systems. One for our fermions and one for our bosons. Right? Because you can imagine, if I'm talking about combinatorics, how many things are where, and how many things are doing a particular thing, it's going to matter whether I can stack them up or not. Right? If I have a gas of photons, and they could in principle all be in the same place, right? They just fly through each other essentially. Well, then I have one type of statistics that's going to dominate. Now, imagine I had a gas of electrons flying around, like a bunch of electrons flying around. They can't be in the same place at the same time because the Pauli exclusion principle prevents that. So the statistics of that system are going to be completely different. So now we're going to add two new members to our distribution zoo. So before we had the Boltzmann distribution, and now for quantum statistics, we need a distribution each for bosons and fermions. So for bosons, this is called the Bose-Einstein distribution. This is for bosons, integer spin. Right? After Albert Einstein, obviously, and Savindranath Bose, an Indian physicist. So the distribution for Bose-Einstein, function of energy, and I'm not going to derive either of these just like the other distribution, I'm just going to write them down. And hopefully you believe me. Is given by this. Okay. And then for fermions, we have the Fermi-Dirac distribution, and this is for fermions or half integer spins after Enrico Fermi and I don't remember Dirac's last name. No, Fermi was Italian, Dirac was English, in case you're interested. So the Fermi-Dirac distribution is similar, except you have a plus one. So this E, the alpha, that's the normalization. Okay, when we go to normalize these distributions, this alpha is what we're going to be solving for the normalization, right? And there's reasons to write that as an exponent instead of just a regular number, but in principle you can do it either way. And then the only difference is whether or not we have this minus sign here. Right, and that's easy to remember which one is which because it's the opposite of whether it's symmetric or anti-symmetric. So I have integer spin bosons, they are symmetric states, they get a minus sign, and if I have fermions, they're half integer anti-symmetric states, get a plus sign. So it's the opposite of whether I have a plus or minus here. Okay. So again, this says that fermions do not stack, but bosons do. So that's pretty much all I wanted to get through today. Because these videos got broken up into 3 different pieces, I'm not sure how long I've actually been talking. Hopefully it's not too long or too short. Next class, we will talk about starting to do some applications of these distributions, okay, and our quantum statistics. If you guys watch these videos,